Hello, everyone. My name is Juner Zhu. I'm currently a research scientist at MIT, working jointly with Professor Tom Wizbicki in mechanical engineering and Professor Martin Bezant in chemical engineering. I'm also serving as the co-director of the MIT Industrial Battery Consortium. The research that I am presenting today is mechanical safety of lithium batteries, physics-based models, data-driven approaches, and their intelligent combination. One of the scenarios that we are interested in is electric vehicle accidents. You must have seen this picture in social media. It's about a burning Tesla on a highway. So what happened? According to the accident report, a tow hook from a truck hits the bottom of that Tesla car and its battery pack. Inside that battery pack, one or several battery cells were severely damaged, causing an electric short circuit and the fire of the whole car. Behind this fire is what we call electrochemomechanics, or the interaction between mechanics and electrochemistry. We have mechanical deformation and failure first in this case, inducing the undesired electrochemical reactions, and these reactions in turn generate heat to make the failure propagate. We call it thermal runaway. There have been many nice experimental studies, and the mechanisms of such accidents, in my opinion, is already quite clear to us. However, modeling this accident is still a very complex problem. The complexity stems from three sources. First, the system spans multiple scales, both in length and in time. Here, I'm only showing you the length scale. So the second source of complexity is multiple materials, phases, and physics. At the particle level, we see phase separation, and the electron level, we can define the electrochemistry and plasticity and flow of the granular media, and there are much more, and I just named a few examples. The third source is called curse of dimensionality. In other words, the complexity of the system increases exponentially with the number of variables and degrees of freedoms. So looking at this battery, our team is now able to establish models and theories at each scale, but it is extremely hard to develop one unified model that can cover several scales. So in today's first part of today's talk, I will show you how our team followed a physics-based roadmap to predict the failure of lithium batteries. And the background is the Tesla accident. When an external object hits the bottom of the car, it can deform the battery cells. Indentation tests actually are commonly used to mimic this scenario. And the X-ray CT scanning is now a popular choice to visualize the damage. But a cheaper and sometimes more effective way is to cut the cross-section of the cell, polish it, and do microscopic imaging. There are nice pictures made by our colleagues at Oak Ridge National Lab. So after zooming in, we can see that there is a clear sign of shear fracture of the structure, which causes the mismatch in the contact between the positive and negative electrodes. That means a short circuit. So today time is very limited for my presentation, so I just want to use one slide to show you how the physics-based roadmap look like. In the past 5 years, our team started from micro testing of the battery components. Using the mechanics learned from those tests, we first established an finite element model of the drained layered structure, then extended it to polymechanical by including the flow of electrolyte. Finally, we added electrochemistry and thermal effects. We use those models to reconstruct the EV5 accident, and at the same time, we performed a cell-level damage assessment with X-ray CT scanning to validate our model. So the biggest advantage of this kind of physics roadmap is that it is reliable. Let me take two models out to support my statement. So this is the detailed finite element model of the whole battery cell. every single layer is characterized as a continuum a layer with fine mesh size. Here, I'm showing you the deformation pattern on the cylindrical road indentation, and we can already see clearly that there is shear localization. We also examined the force displacement response taken at the rigid indenter. The solid line is experimental data, and the blue dots are the numerical simulation prediction. We see almost perfect agreement despite a small overshooting in the end. Actually, I want to say that in today's talk, this small figure is my personal favorite because it delivers a very important message to you about physics-based roadmap, which is that as long as the physics is correctly learned, there is no need for computational tricks. We simply put all the layers upon each other and gave them the correct constitutive laws, and the result is already very good. So what is even more exciting is that we compared the shear localization pattern with the high-resolution micro-CT scanning. Again, we found a very good match, which suggests that our modeling of the solid skeleton is very successful. But I still want to point out that this is still not the real structure. Actually, in reality, as I already mentioned, there is liquid electrolyte. During the deformation induced by external load, the electrolyte can be squeezed, and should be micro flows between the particles that can contribute to mechanics. To validate this mechanism, we performed 2 groups of control tests. So in the first test, we performed compression tests on the drained dry solid skeleton samples on 5 different loading speeds. In the second group, we did the same tests on saturated porous electrolyte, which means with electrolyte. So clearly there is a dynamic effect. The stiffness increases with loading speed. Therefore, we developed a poromechanic model, and I'm not going into details, but I can show you the result. Using this theory, I got very good prediction of the saturated porous media, which are the dashed lines here in this slide. So let me briefly summarize the physics-based roadmap, actually the modeling approach. We learned physics at material level, microly, and we developed detailed models to predict the mechanical properties. However, this kind of model is computationally expensive and cannot be used for car simulation. So the question is, can we scale up our success of the detailed models? One way is, of course, we can do that. One way is to develop so-called homogenized models, treating the battery structure as one unified material. Our team has very successful models as well, for example, predicting failure with a homogenized model. In this way, we can actually increase the computational efficiency of the model. However, at the same time, I want to point out that we lost a lot of physics. As I said, learning physics is quite expensive at micro scale. Losing a lot of physics is not what we want. Okay, so recently we have seen a lot of progress in a powerful tool called machine learning. So we ask ourselves, can we scale up physics-based models with the help of machine learning? Our first impression of machine learning actually is it is a powerful black box. We parameterized the car crash problem and made use of our high fidelity detailed model of the battery cell and generated 2,600 simulations. We labeled the result as a short circuit or safe condition according to whether there is a crack in the separator. And then we randomly divided all the data into 8 groups. 7 were used for training and the remaining 1 for testing. We tried different machine learning algorithms and got 1 classification model and 1 regression model. The classification model finds out which is the safe range for the battery to operate and which range is will cause a short circuit and even fire. And the regression model can tell us how far away we are from that undesired accident. So this is actually a typical example of a data-driven model. So what we use is over 2,600 cases as input and the output is called a safety envelope that can be used by the EV battery management system to make decisions. At the same time, we are also improving our training data. On the one hand, we are developing a robot to do real battery tests at ETH. And on the other hand, we are working with Unreal to make use of their open source data. So from this example, actually, I want to say that we can see that there is a clear limitation of this kind of data-driven approach. So the limitation is that its applicability depends on whether you can get and obtain and afford a big data or not. So this is a big limitation. Then I started to rethink this situation. So actually data is actually not the only thing that we have. What else do I have? So clearly we know some of the physics of the model, right? So this is actually my part one of the talk. So why not implement some already known physics into data-driven approach? Okay, of course, I'm not the first one who come up with this kind of idea. Some pioneering algorithms has already been developed and got initial successes. For example, Rice's paper, in my opinion, is probably the first who proposed the idea of physics-informed neural network, or people call it PIN. They studied the flow of incompressive flow, and as we know, the physics here is Navier-Stokes equation, and the authors solved it to predict the pressure field. So another example is Lu's work here. They used PIN to solve the diffusion equation and other equations as well. In their approach, the concentration field here is described by a neural network, and input are the spatial coordinates and time, and the partial differential equation, initial and boundary conditions were described in the loss function. By minimizing the total loss, they got an approximate solution of the PDE. And based on this kind of algorithm, actually the authors established an online library of PDE solvers. So given this success, we revisited our power mechanics model of the battery with the PIN PDE solver. So we constructed also a neural network to approximate the displacement field of the solid skeleton and the velocity and the pressure of the liquid electrolyte. In this case, the known physics is the power mechanics model that I mentioned in the physics-based roadmap. But here, for simplicity, we only consider the elasticity case. Even so, there is already a lot of residuals and coming from the governing equations and boundary conditions. We then smeared all of them into one loss function and introduced a weight vector to unify it. And then we minimize the total loss function to get a prediction. We find that the pressure prediction agrees quite well compared to our simulations. So this framework appears quite simple and effective, but the reality behind it is that we can obtain using this kind of framework. What we can obtain is highly depends on the hyperparameters, how to tune the hyperparameters, especially this factor, weight factor in our case. Okay, and it took actually us even several months to get a very good, reasonable result. So the question is how to determine the hyperparameters, which is very painful. So we carried out a very careful study on a simpler case, which is an elastic plate under in-plane loads. Now this is a 2D problem, and the residuals are just forced by balance equation in two directions and four boundary conditions. The weight factors here are just like 6 components to be determined. We compare two ways. One is optimization, tuning these parameters, and we compare it to FE simulation. And the other way is that we formulate the total loss function, use the energy method. Here it is the potential energy. I'm not going into details, but showing you the result will be, I will provide the results only. And we can see that in this simple case, the prediction of these two methods is equally good. But to push the algorithms more to their limit, we introduced a hole into the center of the sample. Now we can see that energy-based method correctly predicts the stress concentration. However, even after 30 iterations of hyperparameters optimization, we still did not get a good prediction. And to push even more, we carried out a 3-hole tension test simulation, and the comparison conclusions are the same. So based on this pilot study, we found that the conclusion is that following the physics meaning of the hyperparameters can help us greatly help us to find their values. In this case, physics is the energy principle. Okay. So let me briefly summarize, because time is very limited, summarize my presentation. There is trade-off between physics and data. And at micro scales, data available to us is very small, but physics can usually be clarified. With the physics-informed neural network method, we can now implement the physics into algorithms and give the prediction. But at the macro scales, physics is usually hidden behind the big data. If data is accessible and affordable to us, we can make use of the purely data-driven method and get predictions as well. But in reality, more often, we know some physics and some data. What I did not show today is that we can also make use of develop hybrid algorithms. For this type of hybrid models, we seek the intelligent combinations of physics-based and data-driven approaches. So, okay. So at this point, I would like to close my presentation and thank you for presentation. Thank you for attention. And I also want to thank all our team members, collaborators, and our sponsors. Thank you.